Hello and welcome to the third part of our video lectures on how selection impacts allele frequencies. Now, we've already looked at two situations, one where we did selection for the dominant, and if you remember in that case, our fitness values were WPP was equal to WPQ, and both of those were greater than the fitness for the recessive homozygote. Now we also had a situation where we had selection for the recessive, and that looked similar in that the WPP, the fitness of the A1 genotype, was equal to the fitness of the heterozygote, but in this case the fitness of the A2 genotype was greater. Now, just looking at these, you should be able to see that there are at least two other options we could end up having with respect to how the fitness values relate to each other. We could have our homozygote for the A1 allele being greater than the fitness of our heterozygote, and the fitness of our A2 individual, the recessive genotype, is also greater than the heterozygote. This would give us selection for the homozygotes. Alternatively, we could see a situation where we have the fitness of our homozygotes being less than the fitness of our heterozygote. This would be heterozygote advantage. And you'll often see this referred to as hybrid vigor as well. So let's take a look for a minute and think about what our fitness values were in these situations. In this case, for our dominant, we had 1 plus S equals 1 plus S is greater than 1. Here we had 1 equals 1 is less than 1 plus S. Now, in our selection for homozygotes, we have to add another letter because we don't necessarily know that the fitness of this homozygote is going to be equal to the fitness of this homozygote. So this time we're going to say it's 1 plus S is greater than 1, and 1 is less than 1 plus T. Now, if you remember, I told you guys that most of the time we take our lowest fitness value as equal to 1. However, that makes it difficult to work with the situation of heterozygote advantage because we need to have a different fitness value for both of these individuals. So somehow we have to make sure that the fitness value of our A1 individual is less than our fitness of the heterozygote, and the fitness of the A2 individual is less than the fitness of our heterozygote. And these two fitnesses might not be the same. The easiest way to do that is to think of this equation, or think of the relative fitnesses as selection acting against the heterozygotes so that we create a selection coefficient. So we create a selection coefficient that's negative. So we have 1 minus S is less than 1, and 1 is greater than 1 minus T. So when we look at selection for our homozygote, S and T are both greater than 0. When we look at selection for the heterozygote, we have S and T both being less than 0. So now in this case, the interesting thing is that our fitness value at its greatest is 1, and the fitness values of either one of the other genotypes is actually going to be less than 1. So let's take a look at the graphs that we would expect of our fitness values relative to the frequency of P under both of these cases. So if we think of our graph here, of what the frequency of the A1 allele is and what it is relative to the average fitness we see in the population for both of these situations, well, we know that P has to be between 0 and 1. W bar can be a lot of different values, so we're not going to label the axis there with a specific value, and we're just going to take a look at what the points are relative to each other. Now we're going to start out with the simplest case, where the two selection coefficients are equal to each other. That means that the fitness of an A1A individual is equal to the fitness of an A2A2 individual. So where will we have the highest average fitness in this population? Well, if we have 100% A1 alleles, or P is at 1.0, we will have a fitness that's 1 plus S. Now, since S and T are equal to each other, if we have 0 P alleles, that is, A1 is not in the population at all, that must mean that we have 100% A2 alleles, so the only genotype we have is QQ. Then our fitness is going to be 1 plus T, but since S and T are equal, it's going to be at the same point. Now, where will the minimum value be? Where will our average lowest fitness be? Well, the heterozygotes have the lowest fitness. And so when we're going to find the lowest fitness is when we have the most heterozygotes. Now, we should have the most heterozygotes when P is equal to Q is equal to 0.5. That means that the frequency of the heterozygotes that we expect to see is going to be 50%. 2 times 0.5 times 0.5 is 0.5. So in that case, our lowest fitness value for the population, average fitness, should be when our allele frequencies are equal to each other and they're at 0.5. So now we just connect these lines and we get a smiley face. Now if you remember, selection is Sisyphusian. That means it can only move uphill. So if I'm just a little bit to the right of P equals 0.5, say it's P equals 0.50000001, I'll be just a little bit on this side, and selection is going to have to move uphill, so it's going to have to push the P allele to fixation. There's no way around it. Selection will fix the P allele, and it will bring it to 1.0, not asymptotically, but it will fix it because the individuals can't hide in our heterozygotes up here. The heterozygotes have the lowest fitness. Now, in contrast, if we are at just a little bit less than P equals 0.5, say P equals 0.4999999, however many nines you want, that means that selection is going to have to push it up this hill, which is complete loss of the P allele and fixation of the Q allele. So when we have selection working for homozygotes, when they're favored, that means we are going to fix one of those homozygote genotypes eventually. And which one we fix depends on where we start out relative to the midpoint of the system. So now let's take a look at what's going to happen when we look at our heterozygote advantage. The most fit individuals in the population are always heterozygotes, so how can we maximize our fitness? Well, we're going to assume again that S is equal to T again, but remember, we're assuming that those are negative values, so that 1 plus S is actually less than 1, and 1 plus T is actually less than 1 as well. So we have the same thing. P can only be between 0 and 1. And where will our fitnesses be lowest? Well, if we are fixed for the P allele, that means we can't have any heterozygotes. So our fitness value, fixed for the P allele, is going to be at 1 minus S. Because remember, T and S are less than 0. Similarly, if we're fixed for the A2 allele, all individuals have to be A2, therefore their fitness is going to be in A2, that's going to be at 1 minus T. and 1 minus t and 1 minus s are equal again in this example. So where will our fitness be highest? Our fitness is going to be highest when we have the most heterozygotes. And where are we going to have the most heterozygotes? We're going to have those when p equals 0.5 again. So that means our value is going to be up here somewhere. So if we connect our lines, we can see that we get a shape something like this. When we have selection for the homozygotes, we get a smiling face. When we have selection for the heterozygotes, we have a frowning face. Now my question for you is, the average fitness here going to be 1.0? Because that's what the fitness is for the heterozygotes. Well, we won't actually ever reach 1.0 unless S and T are lethal. Because as long as S and T, whatever these selection coefficients are, if they aren't such that you die before reproduction if you are a homozygote, that means there will always be some homozygotes around, because if you remember your Punnett square, every time we have a heterozygote mate with a heterozygote, 50% of our population comes out as homozygous and 50% comes out as heterozygous. So our population will never reach 1.0 unless S and T are equal to, well, I'm not going to tell you that. That one you've got to figure out on your own. Where would we have it so that when S and T are equal to what value could we actually have W bar being 1.0? Okay, so now let's take a look at these graphs for a minute. We have special names for these 3 points. And these 3 points are called equilibrium. We have 3 equilibria. 1, 2, I'll just put in EQ here to remind you, and 3. Here we also have 3 equilibria. 1, 2, and 3. Now, when we have equilibria, we can have different types of equilibria. We can have stable and unstable, and then we can have global and local. Now, how do we define what a stable equilibria is? A stable equilibrium is one such that if you nudge it slightly off of that value, it will always return. So stable, you return to that point all the time. In an unstable, you move away from it. A global equilibrium is one that you always go to no matter where you start. Doesn't matter what your value is, you always end up going to that value. A local equilibria you go to if you are near that value, but you could end up at a different equilibrium. Okay, so let's take a look at our 3 equilibrium points. And we're going to do this by looking at what? The change in P, delta P, is relative to P. Well, we said we had 3 equilibria points, and those are, in this instance, where we have 0, 1.0, and 0.5 as our frequencies. Now, we know we're at an equilibrium when things are not changing. So by definition, if we're at an equilibrium, delta P must be 0. So we know that we're going to have values of delta P being 0 when we only have Q alleles, when we have 50% P and 50% Q alleles, and when we only have P alleles. Because we've defined them up here, those are our equilibria points. Now if we look over at this graph again, okay, let's try and figure out how delta P is going to change so that we can determine if we are globally stable, locally stable, or unstable. Now remember, selection is Sisyphusian. So if I'm a little bit less than p of 0.5, it means I'm going to move towards losing the p allele. So that means my value of p is getting smaller and smaller. Therefore, this has to be at positive and negative side of this graph. So if I am to the left of p equals 0.5, so my allele frequency for the A1 allele is anything less than 0.5, I'm going to lose that p allele. That means my change in p has to be negative because I'm taking p alleles away every time. So I'm going to have negative delta p values for everything between 0 and 0.05. And I represent that by showing my line being below the value of delta p equals 0. Now you can probably figure out what the next side of the graph is going to look like, because if I'm anywhere to the right of p equals 0.5, or as long as my A1 allele is greater than 0.5, selection is going to drive it towards the fixation of the p allele. That means my p is going to be getting higher and higher, therefore the change in p has to be positive all the time. So what we can see is that if I move myself a little bit away from p equals 0.05 in this direction, I'm going to move over here to the loss of the p allele. If I move myself just a little bit over this way, I'm going to lose my q allele, my A2 allele, and I'm going to fix the A1 allele. Therefore, this equilibrium has to be unstable. If, on the other hand, I'm at fixation of p, so I only have A1 alleles, and I move a little bit to the left of that, so I lose a couple of p alleles. So I'm up here. Now notice my delta p is still positive, therefore p is going to be increasing, so I'm going to move this direction. So this one is going to be a local and stable. Why is it local? Because if I was just about here, if I was a tiny little bit below p equals 0.5, now my change in p is negative. My negative taking away p alleles, so I'm going to move to a lower and lower and lower frequency of p until I reach here. So you can see that if I'm to the left of this equilibrium point, of this unstable equilibrium point, I'm going to move to here. If I'm to the right of it, I'm going to move to this direction, to this equilibrium point. Since I have two different equilibrium points that I could reach, they can both only be local. If I move just a tiny bit away from this equilibrium point, will I return to it? So I add a few p alleles into the system. So I have a frequency of p of say 0.05. It's going to put me about here. I look, my delta p value is going to be negative because my fitness is driving me upwards. Has to go uphill, so I have to go towards loss of it. So I have to move in this direction. I'm going to return here. So I am local and I am stable again. So we have locally stable, unstable, locally stable. I know exactly what's going to happen in this system as long as I know what my frequency of p is. Now, what about in this system? Well, remember over here we had a smiley face for homozygote advantage. When we had heterozygote advantage over here, we had a frowny face. So it's the exact opposite pattern. So you should probably be able to guess that we have an equilibrium point here. We have an equilibrium point here. And we have an equilibrium point here. Why are they equilibriums? Well, if we have no p alleles, we can't get any heterozygotes. Because if we're only having A2 individuals breed with A2 individuals, we'll never get a heterozygote. We'll never have an A1 allele, so we can't leave that spot. Similarly, if we only have p alleles, we'll never be able to make a heterozygote. We don't have any q alleles in the system at all, therefore we're stuck there. Our change in p is going to be 0 here, and it's going to be 0 here. And why is it an equilibrium when we're at p equals 0.5? Well, remember, selection is Sisyphusian. It can only move uphill. Once I'm at my frequency of p equals 0.5 with heterozygote advantage, if I were to move to the left, I'd be going downhill. If I were to move to the right, I'd be going downhill. That means selection would be making the population less fit, and that can't happen. So we know that this has to be an equilibrium point as well. So what's going to happen here now? Well, as I pointed out, our patterns are the opposite in what the average fitness looks like. So we can bet our patterns are going to look the opposite here as well. Let's take a look at why that's going to be the case. If I am just a tiny little bit away from fixing the Q allele, because remember p equals 0.0 here, if I'm just a tiny bit away from that point, selection is going to take off, and it has to always walk uphill, pushing that giant boulder of Sisyphus. It always has to walk uphill. So that means the frequency of p is going to be getting larger and larger and larger and larger. That means delta p, the change in p, is going to have to be positive. Rate at which it's increasing is going to get slower and slower and slower and slower until it reaches p equals 0.5, at which point it's going to be 0. So my graph is going to look like this for the values where p is less than 0.5. In contrast, then, if I'm just a tiny little bit away from fixation of the p allele, I have to move uphill again. Sisyphus has to push his boulder this direction. That means my p A1 alleles are getting smaller and smaller and smaller. That means the change in p has to be negative, and I get a graph that looks something like this. So we see that this graph is the opposite of this graph. This graph is the opposite of this graph. Our fitness graphs are exactly opposite, and the change in p-values are exactly opposite. Now we still have three equilibria here, and we need to try and decide what they are. So first of all, we'll take a look at this one. We're at the fixation of p. If I move just a tiny little bit to the left of fixation, so I throw in one Q allele somehow, however it might happen, that means I am now going to be at p of something less than 1, and when that's the case, my delta p is negative. That means I'm going to be getting smaller. The A2 allele is going to be increasing. The A1 allele's frequency is going to be decreasing. So we are going to move in this direction, which is the equivalent of moving uphill over here. So if I'm a little bit off from this equilibrium point, I move away from it. That makes it unstable. Same situation over here. If I move myself to just a little bit to the right of complete fixation of the A2 allele, I can see that my delta P is positive. That means it's going to be increasing. That means I'm going to be pushing uphill, which is what we want. Selection says we have to be going uphill. And we're going to keep getting more and more P in alleles. And so we move away from this equilibrium point. Therefore, it too must be unstable. Now here, this is the interesting one. So we have two unstable equilibriums here. As soon as I move off of them, we're going to move away from them. That means that no matter where I am on this graph, as long as I'm not fixed for either allele, any other place in there, I'm always going to move to this point. So that's going to make this one global. I always approach it as long as I'm not stuck at another equilibrium. And is it stable? Well, if I move a little bit off of it, I get pushed towards it. If I move a little bit off of it this way, I get pushed back towards it. So it's a global stable. So when we look at our situation here, we have under heterozygote advantage, we're going to try and maximize the number of heterozygotes that we have. The selection is going to walk away from trying to fix either allele. It's going to maintain genetic variation in the system, and it's going to produce two equilibrium points that are unstable and one equilibrium point that's globally stable. In contrast, under homozygote advantage, as long as we are not at exactly p equals 0.5, we're going to fix either the Q allele or we're going to fix the P allele, depending on if we're to the right of p equals 0.5 or to the left of p equals 0.5. So when we look at what's happening with our population, we have two locally stable equilibria and one unstable equilibrium. Now this was under the assumption that S and T were exactly the same. And that's not always going to be the case. What's going to happen in these two scenarios if S and T are not equal to each other? Well, we'll take a look at that now.